the 2002 National Electrical Code, specifically Section 215.8, there was a requirement mandating the use of an orange-colored wire for the high leg, sometimes referred to as the Stinger leg or wild leg, of a 240/120-volt three-phase delta system. This requirement meant that any conductor serving as the high leg in such a system had to be identified with orange insulation or marking. The intention behind this rule was to provide a clear and easily recognizable visual cue to electricians and other qualified personnel, indicating the presence of the high leg and its associated higher voltage to ground. This was crucial for safety reasons, as the high leg voltage differs significantly from the other phase conductors in the system and can pose a shock hazard if not properly identified. However, the 2005 National Electrical Code saw the removal of this specific requirement from Section 215.8. This change meant that the mandate for using orange wire for the high leg was no longer in effect under the NEC. It is important to understand the implications of this change and the current state of the code regarding high leg identification. Currently, there is no specific requirement in the NEC mandating the use of orange-colored wire for the high leg of a 240/120-volt three-phase delta system. While the previous requirement provided a standardized method for identification, the absence of such a mandate does not mean that identification is no longer necessary. It simply means that the NEC leaves the method of identification open to other means as long as the chosen method is effective and meets the general requirements for conductor identification. There are several reasons why the NEC might have removed the specific orange wire requirement. Firstly, it is possible that the code-making panel felt that the requirement was too restrictive and did not allow for sufficient flexibility in the field. Different jurisdictions or specific applications might have unique circumstances that made the use of orange wire impractical or undesirable. By removing the mandate, the NEC allowed for alternative methods of identification to be used in these cases. Secondly, the code-making panel might have believed that other existing requirements in the NEC were sufficient to ensure the safe identification of the high leg. For example, the NEC contains general requirements for conductor identification, such as marking conductors with color tape or other means. These general requirements, when properly applied, can be effective in identifying the high leg even without the use of orange wire. Thirdly, the removal of the orange wire mandate might have been influenced by industry feedback or changes in best practices. It is possible that electricians and other qualified personnel found the orange wire requirement to be problematic in some way, or that alternative identification methods were gaining acceptance in the field. The NEC is a dynamic document that is regularly updated to reflect changes in technology, industry practices, and safety concerns. Regardless of the specific reasons for the change, it is important to understand the current state of the code and to follow the applicable requirements for conductor identification. Even though the NEC no longer mandates the use of orange wire for the high leg, it is still crucial to properly identify the conductor to ensure safety and prevent accidental contact with the higher voltage. There are several methods that can be used to identify the high leg in a 240/120-volt three-phase delta system. Firstly, the NEC requires that all conductors be properly identified as to their function. This can be accomplished by using colored tape, marking pens, or other suitable means. When identifying the high leg, it is important to choose a color that is easily distinguishable from the other phase conductors. While orange is no longer mandated, it can still be used as a means of identification. Other common colors include red, yellow, and blue. Secondly, voltage testing can be used to identify the high leg. In a 240/120-volt three-phase delta system, the high leg will have a voltage to ground that is approximately 208 volts. The other phase conductors will have a voltage to ground of approximately 120 volts. By using a voltmeter to measure the voltage between each phase conductor and ground, the high leg can be easily identified. Thirdly, the system should be properly labeled to indicate the presence of a high leg. This labeling should be placed at the electrical panel and at any other points where the conductors are accessible. The label should clearly state that the system has a high leg and should indicate the voltage to ground of the high leg. In addition to these methods, it is also important to follow safe work practices when working with electrical systems. Firstly, always de-energize the circuit before working on it. Secondly, use appropriate personal protective equipment, such as gloves and safety glasses. Thirdly, be aware of the potential hazards associated with working with electricity and take steps to mitigate those hazards. While the removal of the orange wire mandate from the NEC might seem like a minor change, it has important implications for the safe identification of high legs in 240/120 volt three-phase data systems. By understanding the current state of the code and following the applicable requirements for conductor identification, electricians and other qualified personnel can ensure the safety of themselves and others. In summary, while the 2002 National Electrical Code mandated the use of orange wire for the high leg of a 240/120 volt three-phase delta system, this requirement was removed from the 2005 National Electrical Code. Currently, there is no specific requirement in the NEC mandating the use of orange wire for the high leg. However, it is still crucial to properly identify the high leg using other means such as colored tape, voltage testing, and labeling. By following these practices, electricians and other qualified personnel can ensure the safety of themselves and others when working with these systems. The NEC, or National Electrical Code, serves as the benchmark for safe electrical design, installation, and inspection to protect people and property from electrical hazards. It is developed and updated every 3 years by the National Fire Protection Association, or NFPA, through a consensus-based process involving various stakeholders, including electrical contractors, engineers, inspectors, manufacturers, and other experts in the field. The code covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. The purpose of the NEC is to provide a comprehensive set of rules and guidelines that, when followed, will result in a safe and reliable electrical system. It is important to note that the NEC is not a law itself, but it is widely adopted by states and local jurisdictions as part of their building codes. This means that compliance with the NEC is often legally required. The NEC is organized into chapters, articles, and sections, each addressing specific aspects of electrical installations. The chapters provide a broad overview of the topics covered, while the articles delve into more specific requirements. Sections provide detailed rules and specifications that must be followed. Some of the key chapters in the NEC include Chapter 1, which covers general requirements, Chapter 2, which covers wiring and protection, Chapter 3, which covers wiring methods and materials, Chapter 4, which covers equipment for general use, Chapter 5, which covers special occupancies, Chapter 6, which covers special equipment, and Chapter 7, which covers special conditions. Within each chapter, there are numerous articles that address specific topics. For example, Article 210 covers branch circuits, Article 220 covers branch circuit feeder and service calculations, and Article 250 covers grounding and bonding. Each article is further divided into sections that provide detailed rules and specifications. For example, Section 210.8 covers ground fault circuit interrupter, or GFCI, protection for personnel. Section 220.12 covers general lighting loads, and Section 250.50 covers grounding electrode systems. The NEC also includes informative annexes that provide additional guidance and information. These annexes are not part of the enforceable requirements of the code, but they can be helpful in understanding and applying the rules. For example, Annex C provides examples of conductor ampacity calculations, and Annex D provides examples of dwelling unit load calculations. To effectively use the NEC, it is important to understand its organization and how to navigate the various chapters, articles, and sections. It is also important to be familiar with the definitions of key terms and concepts used in the code. The NEC is a complex document, and it is not always easy to find the information you need. However, there are several resources available to help you. Firstly, the NEC itself includes a detailed index that can be used to quickly locate specific topics. Secondly, there are numerous handbooks and guides that provide explanations and interpretations of the code. Thirdly, there are online forums and communities where you can ask questions and get help from other electrical professionals. The NEC is constantly evolving to reflect changes in technology, industry practices, and safety concerns. The code is updated every 3 years, and each new edition includes revisions, additions, and deletions. It is important to stay up to date with the latest edition of the NEC to ensure that your electrical installations comply with the current requirements. Some of the key changes in recent editions of the NEC include revisions to the requirements for arc fault circuit interrupter or SI protection, updates to the requirements for surge protection, and new requirements for energy storage systems. These changes are intended to improve the safety and reliability of electrical systems. In addition to the NEC, there are other standards and codes that may apply to electrical installations. These include standards developed by organizations such as Underwriters Laboratories, or UL, the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These standards provide specifications for electrical equipment and materials, and they are often referenced in the NEC. Compliance with these standards is important to ensure that electrical products are safe and reliable. The NEC is an essential resource for anyone involved in the design, installation, and inspection of electrical systems. By understanding the code and following its requirements, you can help to ensure the safety of people and property from electrical hazards. It is important to stay up to date with the latest edition of the NEC and to seek out additional resources when needed. With the right knowledge and skills, you can create safe and reliable electrical systems that meet the needs of your clients and customers. When working with electrical systems, it is essential to prioritize safety at all times. Electrical hazards can cause serious injury or even death, so it is important to take precautions to protect yourself and others. Some of the key safety practices to follow when working with electricity include, firstly, always to energize the circuit before working on it. This is the most important safety practice to follow. Before you begin any work on an electrical circuit, make sure to turn off the power at the breaker or disconnect switch. Use a voltmeter to verify that the circuit is de-energized. Secondly, use appropriate personal protective equipment or PPE. PPE includes items such as gloves, safety glasses, and arc flash suits. These items can help to protect you from electrical shock, burns, and other injuries. Thirdly, be aware of the potential hazards. Electrical hazards can include shock, arc flash, and explosions. Be aware of the potential hazards in your work area and take steps to mitigate those hazards. Fourthly, follow safe work practices. Safe work practices include things such as using insulated tools, keeping your work area clean and dry, and avoiding distractions. Fifthly, get training. If you are not properly trained in electrical work, do not attempt to do it yourself. Get training from a qualified instructor before you begin working with electricity. It is also important to be aware of the specific hazards associated with different types of electrical equipment. For example, working with high voltage equipment can be particularly dangerous. High voltage equipment can produce lethal shocks and arc flashes. When working with high voltage equipment, it is important to follow all safety precautions and to use specialized equipment. Another common electrical hazard is the risk of ground faults. A ground fault occurs when electricity flows through an unintended path to ground. Ground faults can cause shocks, fires, and equipment damage. Ground fault circuit interrupters, or GFCIs, are designed to protect people from ground faults. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. It is important to test GFCIs regularly to ensure that they are working properly. In addition to the above safety practices, it is also important to follow all applicable codes and standards. The National Electrical Code, or NEC, provides comprehensive requirements for electrical installations. Compliance with the NEC is essential to ensure the safety of electrical systems. When working with electricity, it is always better to be safe than sorry. By following the above safety practices and by being aware of the potential hazards, you can help to prevent electrical accidents and injuries. Remember to always prioritize safety and to take the time to do the job right. By doing so, you can help to create a safe and reliable electrical system. The information provided in this narration is intended for informational purposes only and should not be considered as professional advice. Always consult with a qualified electrician or other professional for any electrical work or projects. Electrical work can be dangerous, and it is important to take all necessary safety precautions. The narrator and the producers of this narration are not responsible for any injuries or damages that may result from the use of this information.